Hello? Today, we'll dive into the fascinating world of neural networks, and I'll explain why spiking neural networks are promising to be a revolution in the world of artificial intelligence. For those who are already thinking about turning off this video, here's a spoiler. It's because they model the operation of neurons in our brain much more effectively. But let's go over everything in order. The history of neural networks began almost simultaneously with the dawn of the computer era, immediately after World War II. The main idea was to create models that mimic the operation of the human brain. The first such model was the perceptron. Due to the lack of significant computational power, this model was far from what happens in our brain. Then, convolutional and deep neural networks appeared on the scene, which moved even further away from modeling human neurons in favor of achieving results. And they indeed made a real breakthrough, including victories over humans in chess in 1997 and in Go in 2016. The approaches embedded in these technologies continue to dominate the world of artificial intelligence to this day. However, modern neural networks face a number of limitations. In this video, we will take a closer look at the main problems faced by traditional deep neural networks and discuss how spiking neural networks offer unique solutions to overcome them. First, energy efficiency. Currently, models like ChatGPT require about 500 megawatt-hours of energy to operate. If such systems were used for processing search queries by a company like Google, it would require about 30,000 gigawatt-hours of energy, exceeding the energy consumption of entire countries, for instance, Croatia, with a population of about 4 million people. Meanwhile, the human brain functions consuming just 20-30 watts of energy. Second, scalability. Today, the largest neural networks have approximately 10 to the power of 12 neural connections, while the human brain has about 10 to the power of 14. To solve more complex problems, the model needs to become more sophisticated. However, with the use of current models, computational power becomes a limiting factor. Third, the need for learning on the fly. The modern approach to training neural networks follows a specific algorithm. For example, to train a neural network to differentiate between cats and dogs in photographs, we use a dataset of 1,000 images of cats and 1,000 images of dogs. After training, we can evaluate its effectiveness. ChatGPT-4, for instance, was trained on data up until April 2023, meaning it knows nothing about events that happened after that time. To update its knowledge, the training process must start from scratch. Unlike these models, humans learn continuously, drawing conclusions and acquiring new skills based on incoming information. To better understand the difference between spiking and classical neural networks, let's examine how a classical perceptron is structured. A neural network consists of layers, and the signal sequentially passes from the input neurons through the intermediate layers to the output. The signal transmission between neurons occurs in the form of numbers. Each connection is characterized by a weight, which is multiplied by the signal magnitude from the neuron. This behavior models the work of the resistor connecting two neurons. In reality, neurons are connected by synaptic connections, representing a complex system with gaps through which the signal is transmitted when a neuron is activated. This process more closely resembles the operation of a capacitor. If we were to measure the voltage at a neuron's synapse, we would see the following. Signals of roughly the same magnitude and short duration. How does our brain work? Imagine you are a neuron. All you know is that you have 5 neuron friends who come to you asking to be activated. Also, you have 5 neuron friends to whom you go in case of activation. Let's consider 2 situations. The first one of your neuron friends comes to you and says, "Activate," to which you respond, "Really? And where are the other 4? And decide not to activate because you are not sure. And the second situation, almost simultaneously, 4 out of 5 neurons come to you and in unison say, "Activate." Here, you are sure that you need to activate and go to the other 5 of your neuron friends asking them to activate. Spiking neural networks operate on a principle similar to biological neurons. They exchange not numbers, but pulses. The key is not a single spike, but a collection of spikes. If the sum of impulses exceeds a threshold value, activation occurs, and the signal is transmitted further. It's important to understand that if neurons are not connected by synapses, they function independently. You, as a neuron, are not aware of the existence of other neurons, except for those with which you have established synaptic connections. The learning process in our brain works as follows. Let's return to the situation where, as a neuron, you receive simultaneous activation messages from 4 neurons. In such a case, you would be grateful for not having to guess whether to activate or not. And in thanks for such coordinated work, you give them a chocolate bars. The next time, they'll be more eager to come to you with an activation message and will arrive earlier. Meanwhile, if only 1 neuron came to you, you would most likely tell it not to rush next time. This process is called Hebb's principle, after the Canadian physiologist and neuropsychologist. Frequent simultaneous interactions between neurons strengthen their connection, while random activations weaken it. Now that we understand how spiking neural networks work, let's discuss why they are capable of solving the problems inherent to classical neural networks. Energy efficiency is achieved because a neuron is activated and consumes energy only when it receives impulses. If it receives an impulse, it performs only a few simple operations, adding the current impulses at the input and comparing them to a threshold value. This is why our brain consumes 20-30 watts, not megawatts. The scalability problem is solved by the independence of neuron operations. There is no synchronizing system that would prevent us from increasing the number of neurons and connections between them as much as we want. The problem of interaction with the environment. Since we do not synchronize neurons, they can independently learn depending on the signals they receive and, simultaneously, work by either passing the signal further or not. In the next video, we will move from theory to practice and try to teach a spiking neural network to play Doom. Thank you for watching. Hit like if you enjoyed the video and subscribe if you don't want to miss the next one. It's going to be interesting.